Good morning. So this week I'm gonna try to cover two chapters, chapters 12 and 13. 12 is on I/O systems, and this should be mostly a review for you because from the beginning we talked about I/O with at Syn 51, but this is just gonna go into a little bit more. Mostly should be a review, so this should go fast. And then chapter 13 is on file system interfaces. That's going to be a series of 3 chapters or so on file systems. But used to be fewer chapters, and the book just decided to divide up the different topics from the more interface separate from the implementation in the more advanced topics. That's why they divided into 3 separate chapters, but each one is much shorter than before now. Okay, so I'm gonna try to finish up I/O systems and then go into the file systems. So we'll take a kind of a review of I/O hardware, application I/O interfaces, and also kernel I/O subsystems, a little bit on how to turn requests into hardware operation and performance. So first, I/O hardware. So this is supposed to be mostly, again, architecture, hardware issue, but then OS book decided to bring this in because OS does have a little bit to do with it. And really it's the interface. How do you control I/O devices from OS? Now there are many different I/O devices, different types for storage, for transmission, for human-computer interfaces. They're all called I/O, but they really vary a lot. What they have in common is they are somehow connected via these ports. A port is really an endpoint for a device to connect to another device. And the way it connects is often via some kind of bus. Bus is more of a shared medium between 2 or possibly more devices. You can think of it as a set of wires, or it could be multi-hop type. And most often there is something called a controller or device controller that resides within that device. Its job is really just to deal with the interface specific aspect of the device. Because the device has its own thing to do. So for example, a disk may need to control moving the arm, and reading, writing, buffering, caching, all that. And then one part is the bus aspect, which then deals with how the bus protocol works. Right? And they operate at very different speeds. So a disk, you may expect several hundred megabytes per second of transfer rate, whereas a human computer interface device, depending on how fast can you possibly type on the keyboard, right? And also even mouse, it's not so high speed compared to a disk. So there's various ways suitable for different speeds of devices. And what OS does is, of course, it can write a device driver for each device. That just deals with, in other words, a set of routines just to access the device from software. But then it's much better to have a uniform structure and to hide the details. And hopefully the interface is the same or mostly the same across different devices. That way you at least have a good programming interface for it instead of doing a very device-specific way to programming. Okay, so I/O interfaces, well, in terms of hardware, there's ports, bus, and controller. So port is, you can think of it as a connection point or maybe an endpoint of connection for a device, and it connects to a bus. Now there's shared bus and there's daisy chained. Shared bus would be one where you have a set of wires that are electrically shared between 2, possibly more of these devices. So Ethernet or traditional Ethernet would be one example where you actually have to really just wire and then multiple computers just tap onto that same wire. And that would be a shared bus. And that way, well, it is simple, but then there's issues with scaling potentially. Now there's also daisy chain. Daisy chain, an example would be like shown on the bottom. So I mentioned the SCSI connection is a daisy chain. So on the back of every device, you have most likely two ports, one coming in and then the other one for chaining a next device, and you keep chaining. So strictly speaking, these different devices only do pairwise sharing, but together that daisy chain is also considered a bus. It's a daisy chain bus, okay? And USB is kind of like that too, except it follows more a tree topology. Firewire, similar, but Firewire can have, I think, potentially loops. So like USB, really you don't have more than two things. You have exactly one side that's upstream, the other side that's downstream. And you can think of it as, maybe not daisy chain, it's more of a tree, right? So there's different versions of these things. And now a controller is really a general term for anything that operates on a port, a bus, a device, or some combination thereof. And a lot of times these may be built in to the device. For example, you have a disk drive or maybe a flash drive. There's actually a controller on there that's built in. You don't see it. It's integrated. But previously, these controllers may be their own board that's separate from the device. And the bus may have its bus controller that's on a separate board. And so if it's one that deals with the bus, or it's sitting between the bus and the device, it's called usually called a hosted bus adapter, right? HBA, or sometimes just host adapter. And so what you need to do from the processor is then you don't talk directly to a device. You actually talk, you send commands or transfer data on the bus. You talk in bus protocol, okay? But the bus protocol itself may embed commands specific to that device. But still, there's different layers of it. So the bus acts as a transport for the command and data, and then your device driver would then send these things over this bus protocol, and then the other side extracts and then interprets those as commands. And this is what a typical PC bus structure looks like. So most PCs now have a PCIe or PCI Express. The little E stands for Express. Now you may have heard of PCI and PCIe. So nowadays it's mostly PCI Express. Previously, PCI was more popular. That was in the 90s when Intel developed it for mainly servers, but quickly PCs all started using it. And even before then, there was different bus standards. But the idea was you have parallel wires running. And that was how they were able to achieve relatively high bandwidth in those days. They didn't know how to clock very fast. So those are parallel buses. But then the problem there is when you have lots of wires running in parallel, you have clock skew, so you can't clock very fast in the first place. And it's bulky. Your connector has to be very big to have several dozen wires. And you have clock skew issues. And so they don't scale as well. So about 5 devices max. And in fact, they're not hot pluggable. So while the PC is running, if you try to unplug one of these, you crash the whole thing. And PCI Express uses serial connection. So it's switched as opposed to shared bus. And switching, I mean, you probably have seen in your home, you have an access point, and that has Ethernet. That's an Ethernet switch in there. And switching allows you to establish a dedicated connection for that duration of that transaction. And it can be fast, and they know how to clock much faster, and there's less issue with clock skewing. It's also hot pluggable, and up to 32 devices, and that's been used since 2001 or so. And of course, there's newer versions of these, but this is pretty much the typical one. And they can do, so PCI bus, the older one, probably 250 megabytes per second. Now, a PCIe, well, you're talking about much larger by gigabytes and higher, right, a second. And so that is kind of the main bus. But then CPU itself, it doesn't seed PCI directly every single cycle. The PCU, what it cares about is really the memory, and then cache is what is that the buffering interface to reduce the memory latency. But if it has to go to PCI, what does it have to do? It has to go through a bus, the bridge, okay? And a lot of time that actually goes through the memory bridge, sometimes I/O, but it has to go through a bridge in order to touch PCIe. And everything else hangs off PCIe either directly or indirectly. Most of them would have a controller. So like a monitor would have a graphics card, right? And that graphics card has a controller and that sits on PCIe. And your disks would, previously would be things like IDE, now most ATA, SATA, and so in this edition they changed it over to SAS, serial attached SCSI, and that would be encompassing a number of different more modern protocols, but still the idea is the same. So your disks don't just sit directly on there. Over this serial attached adapter, and the disk would then hang off that one instead. And there is additional expansion bus interfaces. So for example, your USB doesn't sit directly on PCI. It hangs off an expander like that. And then that expansion bus will be nowadays USB. Previously it's FireWire, there's a few others. And then USB would connect over there. Of course, nowadays with USB Type 3, and then you have Thunderbolt, right? They started shifting just because the speed classes keep changing, and then some of them could attach to the main bus too. But so this way, the relatively slow devices are mostly isolated, and they don't cause interruptions to the high speed, much higher speed transfers. Okay, now how do you actually control a device? Well, so these devices have what's called device registers. Now these registers are different from your CPU registers. So on 8051 you have R0, R1, R2, PSW, right? B, these registers. No, that's not what we're talking about. We're talking about more the registers in the device space. So in the case of 8051, you do have some special function registers or SFRs that are really for the built-in devices. So for example, your UART is considered a built-in device, even though you can think of it as part of your instruction set. Still, logically speaking, it's an external device that happens to be accessible from the processor. But most other things, if you do an LCD controller, you do hard drive, well, there's registers associated with each one of these devices, not in the CPU space, but in the device space. So what do you have to do? You have to then go over whatever protocol that you connect with the bus protocol to then say, I want to access these registers, okay? And so conceptually, yes, you're reading or writing these registers in the devices and to cause I/O to happen. So what are these registers? Well, there's 4 kinds. There's data in, data out, status, and control. Not so surprisingly, because you've done some UART programming on 8051, you would have some idea, right? So if you want to read or write, well, it's the same name as above, but they're really, logically speaking, 2 separate registers. It just happens to be the same name. So when you read, it's a data in. When you write, it's a data write, but you just use the same name as above. But they're really 2 separate registers. So these registers, well, on 8051 you can read and write them directly using a move instruction. But if it's an external device, then you have to then send a little packet over the bus that embeds the read or write. Well, register, you have to name the register because, a register would have a name, and it's most likely some numeric name that or the address. So even 8051 registers R0 to R7, you can think of them as address 0 to 1, 2, 3, 4, 5, 6, 7. Yeah, those devices have their own addresses in the device space, and you read and write them. So you pack up these commands. And same thing with the little SD card. How do you access an SD card? Well, you form these commands to access the registers too. So a lot of times there's these command formats, and so SD card has its whether it's a what's called SPI compatibility mode, or it's 4-bit data and then a few other control bits. Whichever way, there's a format you have to follow, and then read and write accordingly. Now there are registers that are providing status, so that they tell you if the device is busy reading, writing, or it's finished, or if there's an error, and what error it is, error code, right? So those things. And control would be more like settings. You want to set it to different configurations. So for example, if you do communication device, you may want to set it to say, are you full duplex, half duplex, simplex? Do you want parity setting? You want to set a baud rate and so forth, right? Or your Wi-Fi card. Do you want to enable both 2.4 gigahertz and 5 gigahertz, or single band? What do you want to do, right? And how compatible do you want it to be? And you want to enable MIMO and all those, right? And sometimes there's even a disk you can attach to your Wi-Fi base station, right? So, and there's all sorts of things you can do. So those would be done via control registers, and most likely there's more than one. There are probably several, and some of them may be packed together in the same register. And you can do I/O instructions. So what are I/O instructions? Well, you can do instructions that are part of the instruction set architecture. So we've seen in the case of 8051, you have these move instructions that work with I/O ports. Right, so you can say, yes, those are actually I/O instructions. Even though mnemonically they look like MOV, look like another move, they're really different, right? So, and at least if you go to certain spaces, certain numbers, those have special meanings. So those would be called direct I/O, or if you do a move to your general purpose I/O ports, you actually set the bits to 0 or 1. Now, the processors don't always support this kind of built-in I/O or these I/O instructions. So what do they do? Well, they can do memory mapped I/O. So there you use your move or load store instructions to certain memory addresses. Now, these addresses would then have special meaning. Now, they may be assigned by the way the architecture is built, not necessarily the way CPU is built. Okay. So that is, somebody takes a chip, and then if you don't do any special wiring, well, it looks like you have entire memory access, you're not doing any other I/O. But you can also wire up your system so that certain memory ranges correspond to I/O registers. Okay, so from the program's point of view, it doesn't really know. It's just doing read and write or load or store or move instructions. No different from any other memory, but then it actually carries out side effect. It doesn't do the memory load or store. It actually does the I/O instead. Okay, so the way you do it is using load and store instructions, just like any other regular memory. And of course, the cache has to know about that too. So when it sees, oh, that looks like a memory address, the cache shouldn't try to cache any of it. It shouldn't try to intercept it. It should just let it go and then go directly to the I/O, okay? And why would you really need to do that? Well, other than the fact you don't have special I/O instructions, there's actually a need for this too. So sometimes you do want the devices to share memory with the processor. So one example would be like for graphics and even disk a lot of times. So, well, because what you want to do is to tell the disk controller or to the graphics controller, especially graphics, is refreshing dozens of times every second, right? And the graphics card may have its own memory, but sometimes when you write new content, you want it to fetch it. If the processor has to keep writing to the display every time, and it's not a text display, it's a graphical display, then the processor is going to be so busy that doing just graphics updates not going to have any time. So what often happens is then there's a shared memory region between the graphics card and the processor. The processor deposits content there, and from time to time, the graphics card comes and say, okay, I'm just going to grab from there and refresh the screen. Okay, so that way, it really takes a load off the processor, and you get more responsive type of access. And programming is much simpler too. Okay, so now here is an example of how a PC does the memory mapping of addresses of these device I/O ports. So from 0 to F would be DMA controller, 2221 interrupt controller, 4243 timer, and so forth. You can see game controller, serial port, hard drive, and so forth. Okay, so why you need a range? Because remember, there's data in, data out, and also the control and status, right? So you do need some of those. One, I mean, interrupt controller is a separate one. You don't really get all the combinations, but for most of them, you do have some, at least those could be multiple. And so some of them also have the memory addresses as well. And we've seen polling versus interrupt. So now you should know by now, polling, you just use a loop, busy wait, until you get the status you want, and that status change is set by the hardware. It's very simple, and you can write it in a couple instructions, sometimes even one single instruction on 8051. It has a loop and test, right? So now the interrupt is the more common way. Why? Because instead of wasting time polling, all you do, you just set it up, enable the interrupt, processor does its own work. If it doesn't have work to do, it could go to sleep. That's actually better than busy waiting. And when the hardware sets a ready bit, or between instruction boundary, you do the interrupt, right? Saving state, jump to ISR, processor wakes up and to do this, to handle this, right? And so this is, interrupt can be much more efficient. Well, for the most part anyway. And so for polling, you poll if the device is busy until it's no longer busy, so the hardware sets it. When you detect it's not busy, you go ahead and do the sending. And then when it starts sending, hardware sets the bit. And receiving, so it also checks if there's a bit ready to be received. If so, the hardware sets it, and then your polling loop checks it, and then you can read it out. Okay, so the processor needs to make sure data is ready before trying to read, or otherwise it just gets garbage. Now, polling can be easy to write, and in fact, if the device is relatively fast, then polling actually makes sense, right? But most of the time, the I/O is much slower. So if you have a chance, I encourage you to play with 8051 or the ETSIM51. It has this LCD controller, 2-line text, 16 columns by 2 rows, and there's sample code from ETSIM website, and you may have to do a little conversion, but it works. And that LCD is really slow. Okay, and if you try to access it too fast, if you ignore polling, you don't check if it's ready, then you're just gonna get garbage displayed on there. Okay, it's very slow. It refreshes less than 30 times a second. It's very slow, and you don't want to poll it too often either. If you do polling in that case, yes, you could, but then you're gonna waste so much of the process time. It's just very inefficient. So now you can say, okay, so what if I do polling, maybe instead of in the tight loop, I poll at the beginning of one loop, and then If it's not ready, I go and do a context switch to do some useful work, right? And then after I do some useful work, I'll come back and then check again. Can that work? Yeah, it could, but in general, that's not a good idea. Why? Because that's a lot like some kind of cooperative threading, except you inline it, you hard code the threading in there, right? And so, and in fact, you have the danger of not being able to control how much time it takes to do this other useful thing. If it takes too long, you actually can miss events. Why? I mean, think about the UART, right? So yes, it takes a long time for a byte to be shifted in, but then if you wait too long, another byte already comes in, and you're still doing your useful work. You think you're trying to utilize your processor, but then in the meantime, that new byte overwrites your old byte. Okay, and so by the time you come back and check again, well, you already lost a byte, if not more. Okay, so you have that dangerous losing event. Whereas an interrupt notifies you much more quickly. So that's why interrupt could be much better in terms of serving that and not missing out on events. Of course, the premise is that your interrupt service routine shouldn't take too long. Otherwise, it wouldn't have the same issue. So interrupt, oftentimes what happens is you view this as having made some interrupt requests, or IRQ. IRQ is a very common term, especially in PC. A lot of times if older PCs, you see an error message. Oh, this IRQ conflicts with this other IRQ, or some IRQ, what is IRQ, or interrupt request, that's what it is. On devices, it might not be called IRQ, it might be called data ready, it might be called something else. But basically it is a line, it's a signal generated by the peripheral device to notify the processor. And how does it do it? Well, does it set it to a 1? Well, no, most likely it sets it to a 0. It asserts it. It's what's called active low type of thing. So normally, if nothing, it's left high, and there's usually a pull-up resistor pulling it high. And if it wants to make a request, it asserts it low. Okay, pulls down to 0 volts. So why would it do that? Well, it has to do with potentially sharing that IRQ line, because oftentimes the most precious resource on a CPU is its I/O pins, because you can make so many other things very small, but you have only so much room on the outside, and these outside pins take up a lot of room compared to the die on the inside. And so you can't afford, a lot of times you can't afford to have one dedicated IRQ line per device. They may have to share, and I'll talk about that in a little bit. That's called interrupt chaining. And so that means the IRQ line itself is a bus. It's a special kind of bus. It's a 1-bit bus, okay? And so then, but how do you then resolve these different requests? Some device may say, I'm ready, I'm gonna assert the IRQ line. The other devices say, I'm not ready, I'm not gonna assert the line. So what happens? Well, that's why you need this pull-up structure. Why? Because a pull-up is more of a soft one, and it's tied over a resistor. So if you pull it down to 0, what happens? Yes, you actually waste a little current, but the current is limited by the resistor, right? So you don't short circuit, okay? And it allows conflicting values to be driven on the IRQ line. So yes, you allow some devices who are not asserting to just leave it pulled out. But as long as one device wants to request, pulls it down, so you can think of it almost like a AND. Or I should say, it's an inverted of the AND, and so as long as anyone pulls down, so it's a NOR, so to speak, right? So if you pull it down, one or more pulls it down, it's down, okay, and that's asserted. And so when that line is asserted, then the processor sees it, and the processor has hardware to check. And then between instruction boundary, first opportunity flushes the pipeline, jumps to the interrupt service routine, as long as that interrupt is not masked. Remember, you have that EA bit, right? So EA bit could mask or temporarily prevent these requests from coming in. So as long as it's allowed, then yes, interrupt service routine gets called after the state is saved. Okay, and then from that point on, because it's really OS that handles all these interrupts, OS gets control. So the interrupt service routine can then give control back to the OS because it is owned by OS. Okay, vectored interrupt versus chaining, so that's what I was talking about. Ideally, yes, you would like one interrupt IRQ to be associated with every single device, but because the pins are a precious resource, many times these devices have to share an IRQ, to share the same line. So that is with that that mechanism. So the ideal case of one IRQ per device, that's called vectored interrupt. And if you have multiple device sharing, that's called interrupt chaining. Okay, and so then what happens? Well, they share the same IRQ. That means they share the same ISR as well, right? So the ISR gets called because it says, well, that IRQ gets called, that gets asserted. But then what does it have to do? It has to then check with each device individually. Hey, did you call me, device 1? No, I didn't call you. And device 2, did you call me? No, I didn't. Device 3, it has to keep asking everybody individually. Okay, and so device 3 said, yes, I called you. Okay, the service is that. And maybe there's multiple devices. Device 4, did you call me? Well, okay, device 4 also called. And then so that IRQ is shared by potentially multiple devices asserting at the same time. So the same ISR invocation may have to service multiple I/O requests. Okay, so that's what it may have to do. And so it has to query each of the shared devices to see who made the request. And so that's why an ISR could actually spend some time, because imagine having to go through this bridge to a bus to actually talk to the I/O device and then figure out what's going on. And then it may have to do, how many devices do you think can share, right? It could be several. Okay, so this is a figure from the book. You have CPU on the left, I/O controller on the right. And step 1 is the device driver initiates I/O, and then it has to talk to I/O controller, then to initiate the actual I/O. And then step 3, the input ready or output complete or error generates an interrupt signal, right? So it may have to share that with some other devices. Then in the meantime, the CPU is doing its own thing, but then it gets the interrupt when the device sends that request IRQ coming in, and CPU then transfers control to the ISR. The ISR processes, returns, and then resumes. Right? But then, of course, detail is all in there. Yeah.
Professor, if we have multiple devices and we share the same external interruption, and we are going to serve with the ISR, what happens if the ISR is taking too long time and one device is already coming? It's not going to be serviced, that device?
Right. So if you wait too long, you could miss events. Yes. But a lot of times these processors are so much faster that this shouldn't be an issue. Yeah.
But it's something like, it's just optimized by the speed of the processor. It's not there is another mechanism inside of the CPU trying to keep this interruption track.
Right. If you have another interrupt coming in while serving, there's no way it can tell. I mean, other than the explicit query, that's when. So most likely it's going to catch it. But if you're unlucky, yes, you just missed it. That the interrupt came and then you just missed it. Or you query, you're now device 5, but device 1 now asserts its request. Sorry, it has to wait for the next round. But then what's going to happen is it finishes, returns, But if that line is still asserted, it jumps back to that ISR again, right? Yeah. So yeah, but that's kind of an unlucky case. Yeah. Okay, so now this would be event vector table for Intel Pentium processor. So now what this includes is not only I/O, but other things that also use I/O mechanism. So these are errors. They're called exceptions. Okay, and you may have heard exceptions in other languages like Python, Java, C++, and all those, right? So, but here we're talking about the processor level mechanism. So it's really using the same interrupt service routine mechanism, but then these are not external I/O requests. These are internal operations that are triggered by errors. What are some errors? So divide by 0. You could actually set it up so that it jumps to an ISR just to handle that divide by 0. Or if you have a debugger, it could actually set it up so that you hit a debugging point and it jumps to ISR. Or no interrupt breakpoint. Yeah, breakpoint is another one that. So it's you can think of it as really you hit this execution point, it just that ISR takes over. And you can do bounds checking. The device not available, coprocessor segment overrun, invalid task statement, stack fault. So you can set up a threshold for the stack. Page fault is certainly one of them. And then Intel has some secret backdoor in there for their own use. So do not use. And floating point error, alignment, right, and all those. And so, yes, exceptions and traps. Remember traps? Traps are system call instructions. So when you execute a trap instruction or syscall instruction, what happens? Well, the corresponding ISR for the trap instruction takes over, and then because you pass some argument, there's a case statement or switch statement to figure out which routine to go to. Okay? Exception is when you do a divide by 0 or page fault or privilege violation. As part of your instruction execution, not from external event, then it again jumps to an ISR. So ISR is a general mechanism. It doesn't have to be from external interrupt. These internal events can also cause corresponding ISR to be invoked. Now, as you can imagine, handling such a thing could take a long time. So what is commonly done is to divide this handling into 2 phases. It's called split interrupt management, or this 2-level. Well, first is the actual ISR executed. So what it does is it says, okay, I got everything I need. So what happened? Well, divide by 0. Or this request came in, or this other thing, right? So this IRQ got asserted. Then what does it do? It actually then doesn't serve the IO immediately, or it does the minimum needed to grab everything it needs. But then it schedules a separate thread or separate task, whichever. Then so it returns from the ISR as quickly as possible, and later the scheduled thread or scheduled routine then comes and then takes its time to do the scheduling. So for example, that querying of devices, you could do it into this split phase. So first you come in and say, oh, this IRQ got asserted, fine. Okay, I register it, schedule an event, and then I will return quickly. Then later, processor does context switch and all that, and then, but hopefully this one gets handled as soon as possible, but outside the ISR. Then you can think, okay, query this device. Do you have anything? No. Okay. Do you have anything? Yes. All right. And then that way you do that outside the ISR instead of inside the ISR. Okay. So that's the split interrupt management. So first level interrupt handler FLIH. So it does just enough so you can return from ISR as quickly as possible. Second level, the SLIH, it's separately scheduled, but then outside the ISR to do what's needed to complete that that I/O. Okay, so now DMA you may have heard of several times. That's for direct memory access. So that is where you want a controller to offload a lot of the what's called bulk I/O. So what does that mean? So with the say serial port or UART, you're actually doing what's called character I/O, writing a byte and reading a byte. That's 1 byte at a time. Yeah, the processor can deal with that. But what if you're doing like disk read? You're doing like 4K at a time or flash. It's a whole page, if not whole block at a time, right? And those are, well, 4K is 4096 bytes. Or you could do network transfer, Ethernet, right, over 1K, or some of these can, like TCP/IP, it could be up to 60 some K. And so you're doing a lot more. And disk transfer, especially you know with this kind of disk transfer, it's the minimum transfer unit is 1 block, right? That's the OS term for it. It could correspond with sector. But then imagine like you're doing PCIe speed, it could be several gigabytes per second, right? So do you really want the processor to be copying? Okay, you have 1 byte, okay, gotta copy. Ask from the device, put it in memory, ask from device, put it into memory. That's all it's doing. It's gonna be busy doing nothing but moving data 1 byte at a time or 1 word at a time. That's very inefficient, right? Better to say, okay, well, a CPU does what it's good at, processing and controlling. And then with this kind of bulk transfer, it doesn't really take a CPU to do it. Find some assistant to it. Well, this assistant is a DMA controller, okay? So if you're doing 1 byte at a time, that's called programmed I/O. And you would really want to avoid it for these large data movement. So what you want to do is to have a separate controller that does a block move, okay, between device and memory. And so what does it have to do? Well, the CPU does have to tell the DMA controller, okay, let me give you some directions. So basically set up some command. What would it involve? So starting address, and then read or write, and how many bytes? Right? Usually like 512 or some multiples of 2 to the power. And then once it sets up, the CPU goes off and does its own thing. And the DMA controller then sits there and then deals with the device. You have data? Okay, fine, grab it. And then, but then the CPU also wants to use memory, and DMA controller also needs to use memory. Can they use memory at the same time? Not really. So what does it have to do? Well, CPU gets high priority, and CPU has cache anyway. So that means the memory is not busy a lot of the time because of cache hit, right? So that's good, because then the DMA controller sits on the side and say, processor not busy, not using memory, good, I'm gonna steal cycle, okay? And then, so it sneaks in and then does the transfer between devices. And it has its own buffer as well. So that way it can use the memory efficiently and doesn't get in the way of the processor. And the processor gets a cache miss, okay, it goes to memory. And then DMA, of course, has to yield and just back off and then let the processor have priority. Okay, so bus mastering. So CPU DMA can use memory at the same time, but then DMA basically just steals cycles from CPU. But then, what if it's in the middle of a bus transaction? Well, yeah, the CPU can't interrupt it, because otherwise it's wasted cycle. So yes, from time to time, when the stealing cycle, CPU just has to wait until that transfer completes. And then, so yes, that does cause a little bit of slowdown, but in practice, not a lot, okay? So it's much more efficient than CPU having to do the dirty work itself, okay? And then when the transfer is complete, what happens? Well, the DMA controller acts kind of like an I/O device, sends an interrupt to the CPU. It says, I'm done, okay, come, and then CPU, when it handles when it runs the ISR, says, oh great, okay, maybe I set up another block, or does it whichever from there, okay? So the question now is then what kind of memory do you use? So by default, you're running this in kernel mode, and a lot of I/O needs to be protected by. By default, it uses space in kernel or kernel space. But what happens? Well, then, but you're doing this on behalf of the user, right? And so once the DMA, say you're receiving or you're sending, you're using some kernel memory, but then the user may pass a buffer to you, and so then to interface with that, in the system call, then the straightforward implementation would have to then do copy between the user buffer and the kernel buffer, right? And that's wasted time. So then the really more modern systems, they do mapping. Okay, so user code passes some space, and then that gets mapped. And so that way it avoids that copying needed between kernel buffer and user buffer. And there's some DMA controllers that are aware of virtual addresses. That's usually not the case with a lot of these I/O devices, but DMA controllers may be a little more special. And nowadays they're all integrated on the processors. Okay, so steps in the DMA transfer. So you have the device is here, right? So the CPU says, I want this buffer or this drive 2 data to be transferred to memory buffer at this location, address X. Okay, and so the device driver then says, tells it that drive controller, okay, that's what I need to do. So it tells it the location, buffer, and then count. And then it gets out of the way. CPU does its own thing most of the time, cache hit. And then when this count is 0, it does the interrupt. Okay, and then then the CPU gets the interrupt on completion. Okay, so that was more from the hardware view of things. Next topic in this chapter is application I/O interface. So you think in terms of API for I/O, yeah.
DMA 算是 processor 吗？还是不算？
Well, so DMA is what works with devices, and now so there's two parts. The device itself needs to be able to accept commands, and the DMA controller it could, well, so for a lot of microcontrollers, for example, it's integrated as part of the processor, but these processors are more system on chip, okay? And it does need to be aware of memory, so it could be on the CPU memory bus controller here, and it works with the drive controller. Okay, so it takes care of, and these drive controllers, depending on the access mode, it could stream data, but what actually deposits into the memory, it would be the DMA controller rather than the drive controller. So that DMA controller is not part of this drive. It's over here, okay, in the part where it actually interfaces with the memory, okay? It's because it does need to be aware of who needs memory and arbitrate between the CPU and the DMA request. Okay, so, but since it generates an interrupt, you can say, logically speaking, it is outside, but a lot of times it's tightly integrated with the processor and the memory controller.